Hello YouTube. In this video I'm basically just going to define the fundamental theorem of algebra and basically state why it is so profound. Okay, and we can actually thank Carl Gauss for this one. He's my homeboy, but Carl Gauss was the one who basically published this finding. But basically it says this, okay, given a polynomial, we'll call it f of x. Up here in the green we can read it there. It says if f of x is a polynomial of degree n, where n is greater than 0, then f has at least one 0 in the set of complex numbers. That is, as long as it's a polynomial with degree greater than 0, then it is the case that at least one of its roots has to be in the set of complex numbers. And as a matter of fact, we say it has to be a complex number a plus bi, and I'm going to go so far as to say a plus or minus bi. You know, it could be plus or minus. But the bottom line is this. You know, we could start by saying this. Essentially, it means that you have to have roots that are complex numbers. And in red, you'll see here, I've even written, we say, well, if the degree is n, then there are exactly n complex zeros. And I can actually get away with saying that because, well, let's face it, what if my root of a polynomial was 4? 4 would be considered a complex number because we could write that as 4 plus 0i. That would be a complex number in standard form. Or let's say I ended up with plus or minus 3i were my roots. Well, we could also write that as, like, say maybe 0 plus or minus 3i. The bottom line though is this: every number we can think of is complex. But this theorem is so profound because basically what it says is, hey, whatever the degree is, you better be finding that many zeros. Otherwise, you know, you've done something that you need to keep going with. So let's go ahead and take a look. I've written up 4 polynomials here, and actually we can graph them. We go over to GeoGebra here. You know, like, let me get rid of this stuff. I was doing some trigonometry earlier, so we can go View, Grid. Okay, that'd be a good view to have. And you know, honestly, this is, I think, a good enough view right now. Yeah, but our first polynomial we say is f of x equals x minus 2. And I publish these for people to write notes down on. But we say, okay, so looking at this polynomial, first things first, you'll notice that it's degree 1. Okay, and according to the fundamental theorem of algebra, we say, okay, so how many zeros must it have? Well, it must have exactly one complex 0. Now, I would actually also reiterate this. If it's degree 1, it can have at most one real 0, and in this case it has to have one real 0, and it is also a complex 0. So finding zeros, well, of course we would set this equal to 0 itself. We say, well, when y equals 0, what the heck would x have to be? We get that x equals 2. So like nothing shocking here, but the fact of the matter, I just wanted to illustrate it as 1 0. It had 1 0, and that 0, if we look at the graph here, occurs at 2. You can see it right there clearly. Okay, so going back over here, we say, all right, well, first degree 1 0. Let's take a look at this second one up here. So g of x, and I'm creeping up by degree here, by degrees. I love to say that, but okay, so second degree, this has to have 2 zeros. Now, I say it has to have 2 complex zeros exactly. They have to have exactly 2 complex zeros. But that's a little bit different from me asking the question, well, at most, how many real zeros could it have? And we know from our studies of polynomials it could have at most 2 real zeros. Now notice I'm saying that 2 real, purely real zeros. But if it doesn't have 2 real zeros, it's very possible that if we go down by even integers from there, it could have also 0 real zeros, no real zeros whatsoever. If there were no real zeros for this one, then we would say then they would both have to be complex. The bottom line though is this: it has to have 2 zeros. So we say finding these zeros, okay, again, just our method for doing so. This is good factoring review for anybody that needs the refresher on algebra. But we say, okay, so this factors down into x minus 3, x minus 3. As a matter of fact, I'm going to write it as x minus 3 squared. I get a lot of high school kids that like to tell me, well, x minus 3 squared is same thing as well, you can distribute the exponent. It's x squared minus 3 squared, and that's so wrong. Don't do that. But we say this is a perfect square binomial. So if I were to set both of these factors equal to 0, what you notice, I get x equals 3 and x equals 3. In other words, I tend to ask them to write x equals 3, and we'll just say this: it has multiplicity 2. Multiplicity 2. That just means we had a 0 that repeated, okay, of 2. And I think it would be helpful to look at this graph if we go back over here, and we can click off of this object here, and we say, all right, well, what would this look like? X squared minus 6x plus 9. I don't think I've messed anything up there. So there she is. You can see that clearly we have a repeated 0 at 3. And even though it looks like our graph is tangent to the x-axis right there, that's a repeated 0. That's what that would look like. Okay. So hey, degree 2, 2 real zeros in this case, and 2 zeros exactly. Now number 3 here, h of x, we say h of x is equal to x cubed plus 4x. And according to the fundamental theorem of algebra, hey, third degree, you know what this means? It means that, hey, we have to have exactly 3 complex zeros. We have to have exactly 3 complex zeros. However, let's go ahead and ask a different question, a little bit different, subtly different. At most, how many can be perfectly real? At most, how many real zeros can this have? And so since it's degree 3, it could have 3 real zeros, but if it doesn't have 3 real, it's very possible that it has 1 real. So now, either or, I would actually like to look at the graph of this one first. X cubed plus 4x. Okay, this is good review for polynomials. X cubed plus 4x. And you notice this is actually the graph, and I can zoom out here. It is a cubic graph. It's a very slim cubic graph, but you notice it only crosses the x-axis one time, only one time, and that's at 0. And we're about to discover this algebraically. But essentially, what I'd like to get across is this: since it only has one purely real zero, but the fundamental theorem of algebra says, but hey, you have to have 3. So if you only got 1 real one, that tells us the nature of our other 2 roots. It must mean that the other 2 roots that weren't real were actually complex. Okay, that weren't purely real, have to be complex. So we're going to get 1 real root here and 2 complex roots. So let's take a look at this. Setting this bad boy equal to 0, we say 0 equals x cubed. And this is good review also of factoring, because you should always look for a common monomial factor first, or a greatest common factor. You notice I get x times the quantity x squared plus 4. Now, be careful. This is a sum of 2 squares, not a difference of 2 squares. So it's actually, as a matter of fact, not factorable. So at this point, we just go ahead and move on. We say, well, if this times this equals 0, well, then either x was equal to 0, and there's our real 0. We could see it on the graph. Or x squared plus 4 was equal to 0. So subtracting 4 from both sides of this equation, you know, we turn out the fact that those cancel. We have x squared is equal to negative 4. Now taking the radical of both sides, we say, okay, well, now we're taking the radical of a negative thing. So we need to be careful here. We'll put an I out front and say this is radical 4, and then radical 4 is plus or minus 2, so we get plus or minus 2i. The bottom line is this: we turned out 1 real root and 2 complex roots for a grand total of, dun, da, da, fundamental theorem says, 3 roots. You got to have 3. Doesn't matter. You have to have 3. Oh, and by the way, I want to point one thing out, but hey, when you find a complex root, means a couple things. It means, first of all, that you must have been taking the square root of a negative or an even root of a negative. And furthermore, if you were doing that, then you get a plus or minus type of expression. And furthermore, what this means is whenever you get complex roots, if one of them, say, is 2i, then the other one is minus 2i. That is, whenever you have a complex 0, you must also have what we call its conjugate pair. You know, complex roots, they occur in conjugate pairs. They don't have a choice. Okay, it's like if you're a nerd and you like to watch Star Wars or something like that. There's always the Sith Lord, but there's always an apprentice. There are always 2. Okay, they come in pairs. You know, that's really nerdy. I'm really sorry, everybody in YouTube land. Anyways, number 4 here. We say, well, I of x is x to the 4th minus 1. Now this one's like totally a difference of 2 squares. But we say, hey, first of all, we want to recognize this. This is a 4th degree thing. We better be getting 4 zeros. And in terms of commenting on the nature of these zeros, not a bad idea would be to graph this thing. So we say x to the 4th minus 1. There is our power function, x to the 4th minus 1. It looks like a quadratic that's been shifted down 1, except for it's a little bit flatter in here and goes up 1 over 1 still, and it's a little bit slimmer. But anyways, bottom line, people, is this. You see that we have 2 real zeros, okay? And let me see if I can't turn this on for you here. I don't know how long my video is getting at the moment, but we say graphics, axes. We can show the numbers here. I had them turned off for my trig videos. And we say, okay, so you can see it crosses at -1 and 1. So it has 2 real zeros. Now, going back over to here, we say, well, it had 2 purely real, but it's supposed to have 4 overall. So the other 2 must be complex, and we're going to see that algebraically here. So let's go ahead and set this, guy equal to 0. We say, okay, so 0 equals x to the 4th minus 1. Good factoring view, because difference of 2 squares, we could say this is the same thing as x squared plus 1, x squared minus 1, which are, in and of themselves complex, or not complex, but conjugates. And we say that we're not done factoring, because the sum of 2 squares may be static, stuck, but we'd say x squared minus 1 is itself a difference of 2 squares. So now this is about as factored as we're going to get it. We find out that either x equals plus or minus 1, which was verified by the picture. So we say here are 2 real zeros. Recall that, hey, I'm going to pause here for a second. If it's a 4th degree thing, it has to have 4 complex zeros, but we're saying, because of the fundamental theorem of algebra, we're saying at most, how many real zeros could it have? It could have had 4 real zeros at most, but if not 4, then it's going to have 2 or it's going to have 0. We proceed down by 2's from our original number there. And it has 2, so the other 2 must be complex. And solving x squared plus 1, I see this here, x squared plus 1 equals 0. That means x squared equals -1, and square root of both of those is x is plus or minus I, really. We say plus or minus I. But the bottom line is, fundamental theorem, thank you Carl Gauss, says 4th degree, hey, you better be finding 4 zeros, 4 complex zeros. And by the way, keep in mind that complex roots, they occur in conjugate pairs. So just a basic overview of what the heck the fundamental theorem of algebra is saying.